All right. For those who don't know, the Miller-Rabin test is a very popular, reasonably effective, and quite fast primality test. However, it's still really breakable. You can tell from these results, let's say you try a single base 6129 and you're able to find almost 2 million composite numbers that pass the test using that base. So what people tend to do is find optimal bases to combine with such a base that dramatically lower the number of composites which pass the test. Here, for example, when you add 3 more bases, the number of composites drops down to a few thousand. And if you keep going in this case, you can get down to say, let's say 20. Now on the left is a run where more of the action will be shown on what a strong liar is and what combinations of bases might work well. What it's doing now is generating a lot of composite numbers that it can use to break the test. Now, I have to admit there's no shortcut that generates all strong pseudoprimes to a given base, but there are ways to find the vast majority of them. So these logs towards the bottom are showing, as it says, how many numbers that it's still going to generate before it stops generating them. And all these numbers are guaranteed to be composite based on the logic it uses. So it's not like the test is going to be broken in a sense like, oh, this number was a strong pseudoprime, except it's actually not because it really is prime. Of course, it's going to pass the test for all the bases. Yeah, there came the next log. It's exponentially decaying in the number of remaining numbers to print out. So when it gets to about half of that, it will print out again. So this run will use 40 fixed bases. And when at least 19 of them are fooled by a composite number, it will print out which of them are strong liars on that number. And for each base, it will also print the first number in general that fools that base. When this gets done, all of a sudden there will be a big splash from that because that part is really quick. And then later on, it'll show when each base has some other number of strong lies. Yeah, see, there's another level. And then the next one will be 7.6 thousand something. 3803 next, yeah. And boom. So, and actually 240, we know that the first number that fools base 240 is not 3,277, but this will work well enough for these purposes. So yeah, here we go. Stumped these bases. This particular composite number, which might even be a Carmichael number, has fooled lots and lots of the ones used. And then you can see the first number that was tested that fools the first few bases that were tested. And each of these cases is an instance of, let's pick a fixed set of 4 bases and try other bases that go with them that detect composite numbers when the original 4 bases don't. So these 4, for example, are lying on this number, and so does this base. 61, 1487, 288, 117, all lied. 469,935 all lied on this number. However, for these bases, 61, 1487, etc., these 2 bases have not lied on any of the same numbers yet. And then here, yeah, as you can tell, for a single base, again, just as it was in the other run, is not so good. 28,657 composites found to pass the test for each of these other bases, like 62,000, etc., and so on for each of these bases. And further on down, you can see this particular case of 4 bases, 6013, and so on, all of the remaining bases of the 40 that were used have been eliminated. This was the last one. So all of them, there is at least one composite number passing the test with these 4 bases combined with any other base that was used. Now what it's going to do later, it's going to count how many lies each of those combinations has. So even if there is no combination that detects every single composite, there will still be a measure of how honest they are. Yeah, so 46368. Each time each base has that many strong lies, it prints out all those logs. See, some combinations are still alive. This one, these 4 bases have 3 reliable witnesses left so far. That's another thing that it will do. Once everybody's been eliminated, so these were the first 4 that were used in that combination. This was the last one to lie when all 4 of these lied, and it continues to print out additional numbers that fooled that particular combination. It should be most of the way through this by now. There will be a number of stats at the end. Oh yeah, there are still plenty of stump numbers coming up where at least 19 of the bases lie. No, they've all lied at least one. Oh, there we go. This is the last one so far to have all the witnesses eliminated. So these 5 bases actually reached a pretty high first number that they lied on among the numbers used. And then, yeah, the first 8 out of the 40 bases were reliable until this number. But it turns out you only needed 5 of them. Now, again, this isn't quite correct because there exists a smaller number for that particular combination that actually fools all 5 of those bases. And the way that I generated the composite numbers in this run was not going to find it. But it definitely should be logged. These 5. So this combination right here, the 240, 781145, so on. If I cross-check, yes, here's the 781145. It was the last witness eliminated of those. And then you got 34188 and so on. Those 5 bases also lie on that number. And then if you take another look, the second number documented here, 6499, such and so forth, that is the number which is printed out up here. So this particular run found the second known strong pseudoprime to those 5 bases, although in an order of magnitude sense, it's only about for 40% larger than the first one. If someone just picks random bases to run the Miller-Rabin test, you don't get all this exciting stuff. You don't know when something is going to pass your test or how many bases are going to lie. It's just an arbitrary risk that it's going to be fooled. Now it really should be almost done. Here it goes. So, yeah, we saw the log of when the first 8 bases got fooled. So among the first nine bases, no composite number was known to pass. Now notice that this particular one that I had pointed out, which found where I was able to find the second strong pseudoprime to all 5 of them. Among these numbers tested, it only lied on one additional number. It's quite good. And then this first one, for these 4 bases, there was just a single base that was used, which lied on 14 or fewer. Because what this says is that if there were more than 14 lies between 4 bases and some other base, that it won't get printed out. These particular groups of 4 bases did not have any bases to go with them which lied fewer than 15 times. So there isn't anything logged here. And sometimes every once in a while you get a tie. Like let's say you have these 4 and you want to know what to combine with them. Among the bases that I picked, you get an equivalent degree of honesty out of those 2. Whereas for this one, clearly among this sample, 19,423 was the best to put with it. But as usual, the other combination mentioned only had 2 strong lies in this range. Yeah, the number of reliable witnesses was 0, as in no combination of 5 bases didn't lie on any of them, but as the program is able to parse, it figures out which combination had the fewest violations. And then down here, among the 40 bases, generally speaking, how honest was each base? Over 130,000 composites bare minimum passed for a single base. But you can see the variation. Let's see, yeah, see 156,000 to 184,000. The 4 bases at the bottom have square free part 2. Such bases tend to lie more in general, but then you look at this log, for example, 288. Okay, they're not in good shape here in this sense either. because there are 4 of them. There are 4 bases whose square free part is 2, thus they're also ending up towards the bottom in this printout. This is about those stump numbers I was telling you about earlier. At least 19 bases were strong liars for those numbers. And then this counts up how many times each base was a strong liar in those instances. And 288, which is also up there, was not in good shape. Because there are 4 bases whose square free part is 2. If there were only 2 of such bases, or 1 of them, then I expect they would lie a lot less on these numbers. Because in these honest combinations, here's 288, 34,188, at least one of these bases also has square free part 2. Almost every honest combination that I've found has a square free 2 in it. And that's probably why among the 40 bases there were quite a few of them, because normally they would be up here, lying few times. It's just 60,658. Yeah, it's also down there. 532,512 is actually in a better spot. Yeah, look at this stuff. So among the numbers that were sampled, how many strong lies were there divisible by 3, congruent to 1 mod 3, congruent to 2 mod 3, and then the same for 5 and other small primes. You can see the intriguing distribution. 1 mod each prime is the most common. Thank you so much for watching.